Okay. So, this unit, we're going to talk about the other thing that comes out of a chemical reaction, or the other thing that goes into a chemical reaction. Okay? We talked about the stuff, but the other thing we notice about is it gets hot. I see light coming out of it, flames. Hear sounds. And light, flames, sounds, none of those weigh anything. None of those have mass. None of those are matter. They're all energy. Okay? Now, technically what we're studying is called thermodynamics. Thermo means heat. Dynamic means moving. So we're studying how heat moves around. It'll let us do things like predict whether reactions will happen, how much energy we're going to get out of them, right? How far they will go. So, what is energy? I mean, we say burning gasoline releases energy. A battery is stored energy. I don't have any energy today. What is energy? Well, you look it up, they always define it this way. Energy is the ability to do work. And what work means to a scientist is making something move. Pushing it and making it move. The actual definition is force times distance, how hard you push times how far you push that distance. So to a scientist, when I lift the remote off the table, I'm doing work because I'm using force and it's going a distance. If I'm just holding the remote control, I've got force, but there's no distance, so I'm not doing any work. Work happens when I move things. Or when I stop them. If they're already moving, I do what it takes to stop them. So it's how you move things around. Okay, energy is conserved. Okay. What I mean by energy is conserved, well, it's just like mass was conserved. Every bit of mass we started with, we ended with. That was the whole idea between balancing equations. Energy is the same way. Any energy you start with, you end with, it just shows up in a different form. Just like the chemical showed up in a different form on the other side, energy can show up in a different form. Okay? So, say, I needed energy to lift the remote. Where did I get that energy from? I got that energy from the food I ate. There's energy stored in food. Where did the food get its energy from? Well, the food got its energy from the sun. Plants doing photosynthesis. Where did the sun get its energy? Fusion, a nuclear change. If you go back far enough, you will find that energy was created in a nuclear change. But usually we don't go back that far. Okay? So work is force acting over distance. So if I push something and it moves, I'm doing work. If I push something and it doesn't move, I'm not doing any work. If something's moving but I'm not pushing it, I'm not doing any work. So the way we recognize energy is how it changes things. So energy can cause something to move or cause a change that we can see. So technically, energy is the ability to make something move, or sometimes we see it as a change. One thing energy has that mass and matter don't have is a direction. Okay? I can put heat in or I can get heat out. So we have to use words that describe which direction it's moving. Am I heating it up or is it burning me? Okay, so to understand that, we've got to take the big picture view. The universe. Okay? The amount of energy in the universe is constant, according to the law of conservation of energy, except under nuclear changes. Okay? Is divided, but we talk the universe as two separate. I put halves, it's really two separate parts. Because halves implies they're the same size, and they're not. The two parts are the system and the surroundings. And oftentimes, this is just a mental note of which is it, the systems or the surroundings. Just give it a label. Okay, the system is the part you're interested in. If I'm boiling water, it's the boiling water. If it's chemical reaction, it's that chemical reaction. And so the system's the part you're interested in. What's getting hot, what's getting cold, what's using energy, what's releasing energy. And the surroundings are the rest of the universe. The system is usually much smaller than the surroundings. So now that the reason why we identify the system and surroundings, because then we can give energy a direction. And we always take the system's point of view. So I take the system's point of view, is energy leaving or is it coming in? Okay. If the energy is leaving, we call it exothermic. So exothermic reactions, the system releases energy to the surroundings. Ever seen the prefix exo before? You've seen exo at? Exoskeleton. Okay. Exoskeleton is when the skeleton is on the outside. That's what exo means, outside. So if I want to go outside, I go through an exit. Okay. So exo means outside, so that means the heat is going out. So exothermic, it's going out. We do not have exoskeletons. What kind of skeletons do we have? Inside skeletons. Anybody remember the word for inside skeleton? It's endo. So endo means inside. So an endothermic reaction absorbs energy from the surroundings. So a Bunsen burner burning. Okay? Endo or exothermic? Okay, so we're taking the Bunsen burner's point of view. From the Bunsen burner point of view, that flame burning is giving heat out. If I stuck my hand there, I'd get burned because my hand is not part of the system. My hand is part of the surroundings. So if an exothermic reaction happened in my hand, how would it feel? Exothermic means, so the exothermic reaction, that's the system, is happening in my hand.
So you would like,
Is heat going to go in or out of the reaction?
it goes out.
Out of the reaction. So from my hand's point of view, does the heat go out of my hand or into my hand?
Oh,
From my hand's point of view?
no.
Okay.
Yeah. No.
Okay, the reaction is losing the heat. The heat has to go someplace. It goes into my hand. Okay, so notice it's the same heat but a different direction. It depends on what you pick as the system. If I pick the flame to be the system, the heat's going out. If I pick my hand to be the system, the heat's going in. Does that make sense? So it's all about defining the system and then say, which way is it moving? Is the heat going out or is the heat coming in? The energy, do I have to put energy in or do I get energy out? So this would be the ones that you have to put energy into would be the ones that we would write heat on top of the arrow or put the triangle on top of the arrow. And we'll learn why it's a triangle this chapter. Okay? So, ice melting, endo or exothermic? So ice melting.
Oh, so it's your point.
It's the ice's point of view. From the ice's point of view, do you have to put heat in or get heat out when ice melts? Okay, well, let's take the opposite. Let's take my hand's point of view. Okay, if I put an ice cube in my hand, to my hand, is that endo or exothermic? Okay, so is the heat going out of my hand or into my hand? It's going out of my hand, right?
Yeah.
It's got to go out of my hand.
So it's exo?
So from my hand's point of view, it's exothermic. From the ice's point of view, the heat's got to come in to melt it. How do you melt ice? You put in heat. So from the ice's point of view, it's endothermic. So I would say you get to pick your system, unless somebody picks it for you. Like by asking a question, is ice melting endo or exothermic? Well, if they say is ice melting, they're talking about ice melting being the system. Do you have to put heat into ice to melt it, or do you get heat out when it melts?
So the cooler thing is always endo.
The things that make your hand feel cooler would be endothermic. Does that make sense? You don't want to say just cooler, because the way something gets cool is by losing heat. You understand the difference between those two? So it's a challenge, okay? Because you really have to identify that system so you can give it a direction. Okay? So here is a graph of what happens in a Bunsen burner. This is energy, okay? And this is how far along the reaction is. I start off with CH4 and O2. I made carbon dioxide and water. There's complete combustion. Okay? So if it releases energy, that means I have to start with this much energy and end with less energy. So I start with this much and I end up with that much. I lost some energy. That energy was leaving. I get heat out of this. So the graph, starting here, ending there, I end up lower. That means I gave it away. Okay? So this would be the graph of what an exothermic reaction looks like. This is a graph of endothermic reaction. Nitrogen and oxygen make nitrogen monoxide. That's the brown stuff you see out across the valley, because the air that gets pulled into your car engine gets heated up. When it gets heated up, the nitrogen and the oxygen react with each other. And the nitrogen oxide comes out the tailpipe, makes smog. Okay. So I start with low, I end up high. The only way I can go from here to here is to put energy in. If I end up with more energy than I started, then I put energy in. So this would be the graph of an endothermic reaction, because the heat is going into the system. And that's why we get smog. And a catalytic converter tries to reverse this reaction before it leaves. So if you reverse this reaction, it's going to give off heat. So the catalytic converter underneath your car gets really hot. I learned because I was helping my friend throw some bales of hay into the wagon. So you got to go drive out to the farm field. You park your car in the farm field. You get the tractor going, start going, and you look back and there's smoke coming out from underneath your car. And you say, oh, because if you park in the tall grass, the catalytic converter is hot enough to light the grass on fire. The catalytic converters usually get about 600, 700 degrees just to be efficient. And they get hot because this releases heat if I turn it around the other way. So, direction. Every energy measurement has 3 parts. We should be used to 2 of them already. Okay. A number, a unit. Okay, the two units we're going to use are joules, and it says of, it should say or. My finger got lazy, it didn't go up high enough. Joules are calories, two different units for energy. A number, how many. So how much heat, how many calories, how many joules. And that's all we had with all of our measurements so far. And that's because none of our measurements so far had a direction. 28 grams of carbon. What direction is that? Well, it's not going anywhere. Okay? So to tell a direction, we need a sign. Give me a sign. No, not that kind of sign. Positive or negative. So let's go back and look at our graphs. Okay, this was the exothermic one. What sign would you give that change? You start off high and end off low. Is that a positive change or a negative change?
It's negative.
It's a negative change. So if it's exothermic, it's going to be a negative energy change. Because you start with this much, end with that much, you can't destroy it, so it had to go someplace. Start off with a lot, end up with a little. The missing piece had to go someplace. It left the system. It's exothermic. Of course, that means the next sentence is going to say, if it's positive, it's endothermic. Because if you look at the graph of what we said was endothermic, what kind of change is that? Is that a positive change or a negative change? Positive. So the signs match up with the graphs. The signs match up with the graphs. Okay. So in this diagram, what kind of diagram is it? What kind of change is it trying to show you?
Exothermic.
Energy is leaving, so this is exothermic. And notice this, delta E is less than 0. That's another way of saying negative. Delta, this little delta means change in to a scientist. Anytime you see a delta, they're talking about after minus before. How much did it change? So delta means change. Okay, so that would mean this is endothermic, and this delta E greater than 0 means that it's positive. So, measuring temperature. Okay, so we're going to measure temperature. Temperature and heat are not the same thing, so we're not going to use the same unit. They're related to each other, but they're not the same thing. Okay, here's how I can prove to you heat and temperature are not the same thing. Water boils at 100 degrees Celsius, okay, on the Celsius scale. And water freezes at 0 degrees Celsius. That's how Celsius made the scale. He said, I'm going to put my thermometer in ice cube. And where my thermometer is at, I'm going to draw a line, I'm going to call that 0. And then I'm going to take that thermometer and stick it in boiling water. And where it stops, I'm going to draw a line. And he wanted to go metric, but it didn't make sense to just have 10 degrees between freezing and boiling. So he picked 100 instead of 10. That's how he picked the Celsius scale. He got to pick 2 points and how far apart they are. So he picked freezing, boiling, and said, I'm going to draw 99 lines in between.
It's what we use.
And that's what the rest of the world uses. The rest of the world, because I grew up in Michigan, so we would listen to the Canadian radio stations that would come across the lake, and they would say, "Ooh, it's a balmy 37 out today."
That's
Yeah.
hot.
That's hot. See, you guys don't think of 37 as hot. It's hot. 37 is body temperature. It's 98.6. Okay. Hot tub. Hot tub is 40. The hot tub is supposed to be 40 degrees Celsius to kill all the right germs. It's 104 Fahrenheit. Okay. This room is usually between 20 and 25 degrees Celsius. A cool room is 20, a warm room is 25. Just to give you a sense of where they're at. Okay. So that's one of the two official scales for temperature. There's a second one called the Kelvin scale, named after a man whose title was Lord Kelvin. And, okay. Kelvin starts at absolute zero. There is a lowest possible temperature. And that's absolute zero. It's negative 273 degrees Celsius, negative 492 degrees Fahrenheit. It's cold. And it's the lowest temperature, and we'll see why. Kelvin has degrees that are the same size as Celsius, though. Same size steps, just different numbers next to them. So the difference is they are 273 degrees apart. So if I want to change one into the other, Celsius is Kelvin minus 273. Okay. Or Kelvin equals Celsius plus 273. All you have to remember is that the difference is 273, and Kelvin's always bigger. Or another way to remember it is Kelvin can't be negative, and since it can't be negative, there's only one way you can assure that it's always going to be positive, and that's to add to get to it. So, what is 234 degrees Celsius in Kelvin? So you know the number is 273. The question is, do you add or subtract? Okay. The way I remember is Kelvin's always bigger. So if I'm trying to get to a bigger number, I'm going to add those numbers. 507 Kelvin. Both Celsius and Kelvin are capitalized because the symbols are capitalized because they're named after people. So capital K, capital C. Okay, now for the hard version. What is 134 Kelvin in Celsius? It doesn't look that different. It doesn't. It shouldn't look that different. Same kind of question. I know the number is still 273, but if Kelvin's always bigger, to get Celsius, I should subtract 273.
Minus 136.
can't be right. Because 13 minus 4, or, yeah, 139. It's got to be 139.
So wait, 134 minus
273 should be 139.
Yeah.
You said 136.
Really?
Yeah. Okay, so
I meant 39.
okay, the degree sign. You'll notice Kelvin doesn't have one. Kelvin doesn't have one. Why doesn't Kelvin have a degree sign? Because a degree sign means somebody arbitrarily picked 0. And Celsius did. He said, I'm going to call freezing water 0. He picked 0. Kelvin didn't pick 0. There really is a lowest temperature. And here's why. What temperature is really measuring is the motion of the molecules. Vibrating in place for a solid, bouncing off stuff, moving around in a liquid. In a gas, bouncing off pieces, little pieces moving around. So temperature is about motion, how much the particles are moving. So as I cool things off, they move less and less. But there's a limit to how much I can cool them off because there's a limit to how slow they can go. Because the slowest they can go is not moving at all. Because moving backwards is moving. Does that make sense? So the slowest motion you could have is not moving. And if all that motion ceased, you'd have absolute 0. Now, absolute 0 is one of those things that you get closer and closer to, but never quite touch. Lowest temperature achieved has been within a millionth of a degree Kelvin. It happened in a lab in Colorado. Try to see what happens. And bizarre things start happening when you get really close to absolute 0. The things that stop moving, the electrons stop moving around the nucleus. And all the pieces of the atom fall together into this big clump of stuff that you can't distinguish protons, neutrons, and electrons from each other anymore. And that's called a quantum superfluid. Okay? It's the 5th, 6th, and 7th states of matter. But there's other states of matter besides the 4 we know: solids, liquids, gases, plasma. Plasma's high temperature. There's some quantum superfluids that show up at close to absolute 0. Heck, I was reading an article. They found a new state of matter in between solids and liquids at incredibly high pressures. Last week, they announced it. The states of matter are a little bit more complex than just solid, liquid, and gas. But, so, temperature is different from heat. They are not the same thing. Let me try to convince you of that. And we said the temperature of boiling water was 100 degrees Celsius. Okay? So if I'm making spaghetti and I got a pan of boiling water on the stove, what temperature is that water? 100 degrees Celsius. So a drop of that water, a bubble pops and a drop comes up and hits my arm. What temperature is the water hitting my arm? Pretty close to 100 degrees Celsius, right? And it's going to hurt a little bit. Okay? But what happens if I hit the pan and the pan of water falls over on me? What is the temperature of the water? 100 degrees Celsius. Am I going to have the same effect that I got from just a drop of water hitting my arm? No, I'm going to get I'm going to get burned. There's a chance I could die. No, boiling water like that kills people. Kills babies all the time because they reach up and grab a handle. So that's why you need to learn to put the handles facing backwards because babies like to climb. Ooh, what's that? Shh. Oh, that was boiling water coming down on my head. They usually share really loudly when that happens. Okay, so are we agree that temperature, so one of them can cause more of a change than the other, the drop versus the pan. Everybody agree? Same temperature, both 100 degrees Celsius, different amounts of heat. They're not the same thing. Okay. Temperature gives heat a direction. In fact, if you look up in the back of your book, the definition of temperature, it will say the hotness or coldness of an object. It's a lousy definition. It's really about how the molecules are moving. Okay, and temperature always goes from hot to cold. Always flows spontaneously from high temperature to low temperature. So if I put something hot and something cold together, the hot one's going to get colder and the cold one's going to get hotter. Has that been your experience? Okay. Why? Well, temperature is motion. So the high temperature one, the molecules are moving faster than in low temperature ones. So when I bring them together and they touch each other, the fast ones hit hard on the slow ones and make the slow ones move faster. But that slows down the fast ones. So the faster ones are going to be knocked around the slower ones until they start moving faster, but that's going to slow them down. So you're going to end up at the same temperature for both of them until they're hitting each other just as hard. And then they won't be able to change each other's temperature anymore. So because temperature is about motion, that's why he gives heat of direction. Because the slow moving ones are not going to hit the fast moving one and make it move faster. You're never going to put ice into water until it boils. That's not going to work, right? Okay. So boiling water is 100 degrees Celsius, but a drop of boiling water hurts. A kilogram of boiling water kills. Same temperature, different amounts of energy. Not my. Unfortunately, we have to move on. Okay, so energies can't have calories or can't have Celsius or Kelvin as units because it's not the same thing. So that's why we have calories or joules. So a calorie, with a small c, is the amount of heat to change 1 gram of water by 1 degree Celsius. So a calorie is a pretty small piece of energy. How much do it take to heat up a paperclip's worth of water by 1 degree Celsius? Not much energy. A food calorie is really a kilocalorie. If you look at the box, they always spell it with a capital C. And 1 calorie is 4.184 joules. You don't have to memorize that number. It's on there on your periodic table. So why do they make that distinction with the food calorie? Well, they always tell me, you're supposed to get about 2,000 calories a day. But that's really 2,000 kilocalories. And remember, if I want to go from kilocalorie to calorie, 1 kilocalorie is 1,000 calories.
So 2,000 calories would be a lot if you want to
Be-
eat 2,000 calories.
2 million calories. 2,000 little c calories. So 2,000 big C calories is 2 million little c calories.
So if we would eat 200 calories, like big C calories, that would be a lot.
That'd be little c calories. Okay, so but here's why they do it. Could you imagine saying, doctor tell you got to go on a diet, you can only eat 1.5 million calories a day? Because that would be a diet, because you normally eat 2 million calories a day. That and the word, they didn't want to put the word kill on things with food. Stupid reasons, guys. Just stupid reasons. Okay, so they're going to ask you to do some conversions. And all we ask you to do, the units you want to get rid of goes on the bottom, the units you want goes on the top. So if I had 2260 joules That's how much it takes to boil 1 gram of water. How many calories is that? It's little c calories. What the heck, how did it jump to there? So you can do these with conversion factors. You're going to want to get rid of joules, because that's what you got. I got joules, got to go on the bottom. What I want to turn it into? I want to turn it into calories. What's the relationship? Well, I just looked it up and said 1 calorie was 4.184 joules. You saw that number earlier. So all I have to do is divide the 2260 divided by 4.184, and I got 540 calories. Little c calories. Take the unit you got, put it on the bottom, change it to the unit they asked for. Not new math, just new numbers to put in there. So a granola bar has 190 calories. How many joules is that? So 190 capital C calories. I can't go from capital C calories to joules, but I could go from capital C calories to little c calories. The bell doesn't dismiss you, folks. And then I could go from calories to joules, because 1 calorie is 4.184 joules. So 190 times 1,000 times 4.184.
Renee Solar to guidance, Renee Solar to guidance.
And I get 795,000 joules. Okay. Really hard? Have a good one. Practice those, so tomorrow we'll start working with heat and start measuring it. Have a good one.